I was sharing from first actually.
Ma'am, full screen F4 press. Control plus F4 or F4, ma'am?
No. I'm using WPS, so it's getting. Wait a minute, please. I'll check it. Check into it. Whether it is visible now?
No, ma'am.
I haven't presented. No, I haven't presented yet. Right. It's not working for me actually. I don't know why it is. It is not working actually when it is pressed F4 also. I don't know. I'll check it this way. Yeah. Yeah, whether it is visible full slide?
Yes, ma'am. Visible, ma'am. You can continue.
Yeah, thank you. Sorry for the inconvenience. Today, being an FDP program on AI and machine learning in medical imaging, a Python based approach, I'm going to give you a survey. We are going to divide the parts into two. Part one, which consists of a survey of deep learning approaches to medical applications. Second one, how to use Python in medical imaging. This is what we are going to see in this particular 1 hour. I have segregated into two parts. Shall we move on to the first part? Directly, we will go to deep learning approaches since we are all familiar with what is deep learning, what is machine learning, what is artificial intelligence. So I'm directly moving on to what is deep learning. So deep learning is a combination of your machine learning, which has been worked similarly with a part to your artificial intelligence. The second part is image and volume, which consists of segmentation, counting, and interpretation. The third one is genomics, how we are going to represent. Whatever the data we insert into the learning techniques, we should have an output which will give us a beautiful representation. So it has to be it can be an optimization, it can be a prediction, classification, whatever it is. We are going to use fusion, convolution, deconvolution, softmax function to predict the deep learning functions. The the picture images shows the first one is your MRI. This one is your MRI signature, which helps in identifying. The second thing is logistics representation. See, the first point we have to
Mhm.
go to is logistic regression.
Mhm, ma'am.
Logistic regression. Yes, please.
Ma'am, slide is not visible, ma'am.
Now it is not visible.
Yes, ma'am. Slide is not visible.
Oh, slide is not visible. It's showing me it is presenting. Shall I join using this another link? Sorry, it was an inconvenience I couldn't bear with. I'm sharing the screen, but it is not visible. I don't know what is it. I'm sharing, but I don't know why it is not visible. It shows me sharing. Let me join in this another confusion. Two minutes. Kindly bear with me. Kindly bear with me. 2 minutes. I'll make an arrangement. I don't know why it is not getting shared. Actually, I'm sharing the screen. 'It is not allowing me to share actually. I don't know why.
It's okay, ma'am. Continue session. End of the session, will include the PDF, ma'am. Share your PDF, ma'am.
Okay. It's about logistic regressions. See, if you see the picture, it will be more visible. Shall I post it in the group? Okay, no issues. I'll start. Uh, Regarding logistic regression, it is a supervised algorithm which helps us to have a sigmoidal curve which results in zeros and ones with a threshold value of zero point 0.5. Whatever the inputs we give, it may be a clear data, structured data, unstructured data, whatever it is an sigmoidal curve which gives us an output of zeros and ones. The combination of various logistic regressions combined together will give us a deep learning concept, which is a training of each and every member. So this deep learning also has a plane area of y1, y2, y3, and z1, z2, z3. All the three planes will be accessed in this deep learning. Regarding the hidden layers, what it has had to do is more effective than the machine learning. We can count the number of hidden layers which is present in machine learning, but in deep learning, the hidden layer goes on. Whatever the hidden layer, so it gets trained so easily. We access all the three planes of our reasoning. The next one is the pathology, what we are going to see. Pathology, what is pathology means? It is a study of diseases, how diseases gets affected in human beings, not only in human beings, in various animals. Any animals or human beings, we can take this pathology. So here, each and every cells will be detected and secured and will be segmented for each and every acquisition of data. So this pathology, study of pathology is done by doctors, but we people, we computer science or artificial intelligence experts have started to learn this study of this particular data as image. So it is a very huge area which is called as an image processing. We all have known what is the area of image processing is. First, we are going to see in pathology tumor segmentation of tumors. So tumor is a, we all know, a different part of a protrude. It may be a protuberance, it may be a significance object which has been shown in a different style, which is called as tumor. So first we are going to segment the tumor, which is an automated detection of metastasis in hematoxylin and eosin stained whole slide images of lymph node sections, which helps to reduce the workload of the pathologist in subjective diagnosis. So we have got four different type of normal patches, which shows a simple activity. The tumor patches is completely different from the normal patches, which determine the probability that the image patch is a tumor, which can be solved using deep learning models. The next two types of tumor which has been identified, the tumor in both color image as well as our grayscale image. The grayscale image shows the highest node of tumor which has been implemented, and we are going to fix the points as coordinates from x1, y1 to each and every coordinates position has been noted. Secondly, the grayscale images with extension activities will be noted. Each and every coordinate will be subtiled. So this is the high accuracy screen which is reproduced by each and every medical team in various countries, which shows the curve runs from 0.8, 0.8, 0.8654, 0.9156, and 0.9234. This is the high accuracy of the resolution. And how does it work? It is with segmentation of deep learning. So first, we are going to segregate the down sample, what we have received. The pathology report, which is received from the lab as images, will be stored in a data set, which will be retrieved as a CSV file. So each and every image can be scanned, and then it is converted into its grayscale, which downsamples each and every images of the pathology report. The first option is fusion, where it combines each and every member of the report of the data what we have received. Next is the convolution, where the data has been segregated to the hidden layers and has been abducted. Next is deconvolution. After convoluting each and every data, it is once again deconvoluted, so that using the softmax function, the threshold value has been reduced to 0.5. First, the segmentation training is in a progress, which shows the RGB. The RGB shows the natural satellite image what we have procured. The second one is ground truth, which shows each and every label. The blue color shows the building, light green color shows the low vegetation, green color shows trees, yellow color shows cars and clutters, and so on. Likewise, the colors has been segregated in RGB. How machine predicts? Machine predicts through the combination of colors what we have used as a grayscale. The next part is how the network can learn. So network can learn through image patches. So it is WXI plus B, which is a function of FXI, W comma B. The total stretch pixels into the single column is 0.2, which is converted into 56, and there is no tumor at all. When it is a negative value, there is no tumor at all. If the value of the weighted average with the patches increases, it predicts that it is a tumor. Yes, it is necrosis. These are the three various way in how the pixels has been identified. Using softmax function. What is softmax function? It is the exponential value of zj by sigma of c is equal to 1 e power zc. So what is the sigma value? It is a combination of the data what we have, the summation of the data what we have procured, and the threshold value which has been executed. So when the value is less, it shows no tumor. When it is high, it is tumor. When it is negative in softmax function, it announces necrosis. So to predict multiple classes, we have to subject to probability distribution. The next one is simplex method. As we all know, simplex method is a linear method which is used in operation research, which helps in optimization of the problem. So whenever we have a set of data that has to be optimized and has to be minimal, the objective function of our work is to be minimal. So we are implementing simplex problem for the same tumor, no tumor, and necrosis. So for tumor it is 0.13, and non-tumor it is 0.87, and necrosis it is 0. So it is a triangular function of each and every analysis what we have done. It is simplex. The correction of one terms impacts on all. So a minimal part of P of A, the function P of A is corrected so that the value gets changed and it is optimal. The next one is the infinite ways to generate the same output, correction of one stance gradients to another. We can also learn and see classes through this process of elimination. So we can also identify it can be whether it is a tumor, no tumor, or necrosis. Next comes the function softmax and cross entropy loss. So softmax and cross entropy laws always come together, which helps in using in supervised learning algorithms. So here, to predict multiple class, we can project the output onto a simplex and compute the loss here. So it shows no tumor, which is what is the loss of the difference between the for softmax and cross entropy loss is the loss is no tumor is 0, for tumor it is 0.13, and for necrosis it is 0, because we are only predicting, we are segmenting what is whether the report is consists of no tumor or necrosis. So this automatically, this particular data shows 0.13 shows that it has tumor. There are more number of images. Next, we are going for pancreas segmentation. Comparing to tumor segmentation, pancreas segmentation is completely different, because the pathological report says pancreas, we can have it in either sides. In brain, we are going to have it in only for the two sides of the brain. So, but in pancreas, it is a little bit difficult when compared to the brain tumor segmentation. So here the segmentation points has been identified, and it gives you a very huge actions required. So we go for deep learning impacts. So more segmentation, it is more tasks. The first task is FLAR, where the brain or where the tumor, where it is tumor, the lesion or tumor, where it is present. First, we are going to see for subacute ischemic stroke lesion segmentation, it using FLAR. While using FLAR, when it is undergone an MRI scan, it predicts whether it has or not. If it is predicted, there will be a white grayscale images. If it is not there, it will show you a GT. Next, in FLAR, We have a small prediction of a single dot with combined with the GT another dot. Next is TTP, which helps in this is first one is MRI scan, next one is a CT scan, and the last one is here MRI scan of brain tumor segmentation. So first the grayscale is retrieved, next RGB color is given, finally the color of GT is measured, and then the pixel points has been identified. There are multimodal MRI acquisition. Next is multimodal MRI acquisition, because MRI scan reveals the T1 and flare is completely different. The grayscales what we measure is completely different. The second one, CBF, DB, DW, Tmax, and TTP also shows a variety of grayscale images where the pixel points has been identified significantly and can be drawn through the acts. This has been done in all the images of subacute ischemic stroke lesion segmentation, stroke perfusion estimation, and also in brain tumor segmentation. So FLAIR is conducted in all the three areas so that each and every image has accused the level of Tmax and T2 and FLAIR. So some parts may be present missing in each and every pathological report what we have learned. Next, we are going to check on HEMIS, hetero model segmentation. So this has been done in T1, FLAIR, and T2 images. T1 is a CT scan image. FLAIR is an MRI image. So we are going to check what is the hetero model segmentation means. The first hetero model segmentation includes backend, abstraction, and a front end. The backend consists of C1, C2, etc. up to Cn. These are all the levels at which it is going to work. The weighted average and the functions will be calculated in each and every C1, C2 suffixed with 1, 2, and 4, etc. The abstraction level measures the variance and the E value of the C functions. Finally, we have a front end, which is C and C3 and C4. So C1 to Cn, which is a backend, which processes the threshold values as well as the X and Y points, which measures the value. Second is the abstraction, EC squared and variable of the C measured, data measured. Finally, we have the front end as C3 and C4. This is how the images has been scanned using model image segmentation. The results are very blurred images, which is called as BRADs. The BRADs include FLAR, T2W, T1W, T1C, and HEMIS and truth. Always, when compared to the results of a FLAR and T2W, the FLAR has a grayscale image, but HEMIS and truth shows the colored RGB colored image so that we can identify it effectively. T1W also shows a bright image of each and every factors what we have been presented so far. Finally, the T1C has a white image where it is shown as a black dot, the tumor or the identification of disease. The brain tumor segmentation using Brad's 2013 dataset has been displayed. It shows the edema, necrosis, and non-enhanced and enhanced tumors. So each and every subject, there is 5 subjects, T1, T2, GT, T1C, and FLAIR. The method used is Tudition, Jaho, and mere HEMIS has been used effectively. But the leaderboard of this particular brain tumor segmentation is HEMIS, because it shows the complete challenge, because since we have got so much of people having tumors, each and every parts of our body consists of tumors. Tumors is not the clot or whatever we have got. It is an extra functional protuberance or a particular clot, which it may be anything. It may be anything. It is not only a bulging apart or not, etc. It may be anything. So this has been the DICE similarity shows HEMIS is the leader in the challenge, because it has completely verified 88% of the core with enhancing 74. This has been presented in a paper. Next, we are going for chest. So far we have seen the tumors, necrosis, and liver. Now we are going to go on with the chest X-rays, what we have measured. The imaging, how the imaging has been used. First image is atelectasis. Second is cardiomyopathy. Atelectasis is the upper part of the lungs, which has been affected. Cardiomyopathy is the central part of the lungs. Effusion is the final right lobe function. Infiltration is in the left side of your lungs. Mass is in the left, that is the particular lungs part has been affected severely, and nodule is the right end. Pneumonia, the total part of the lungs will be affected. Pneumothorax. These are the 8 ways of interpreting chest x-rays, and this shows using CNN. They have used CNN to do this particular 8 analysis. So first setting, we have gotten AlexNet, the algorithms and convolution neural network predictions using AlexNet is 6.4, GoogleNet is 6.63, VGGNet is 0.62, and RSNet is 0.7. So this has been used in 32,717 patients, and the number of X-rays taken were 108,948 extracts. So the text has been extracted using NLP. So the final shows each and every algorithm what we have been used in convolution net predictions, that is ResNet 50, shows the highest prediction of each and every disease that has been identified in these 8 X-rays. The radiology report, each and every radiology report, we will see only X-rays in black and white. So now the MRI scan or even the MRI Doppler scan shows us color images. So it finds that the left basilar is consolidation and prominent helium is found. The impression small, light, pleural effusion, otherwise the stable abnormal study including left basilar infiltration. So each and every chest has been excuse me, has been used for this. The second radiology report shows no diffusion is nodule. So all the 7 chest images has been implemented with this convolutional neural network, 4 types of networks, and we have attended the results. Next is cell counting. The final one is cell counting of images. We have to count the number of cells which is present in the images. So the first we are going to take image as an input, the pixel rate should be 256 into 256, so that it will be able to input into the network. Next is the convolutions. Convolutions, each and every side, there is 2 sides of convolutions with 32, and the prediction map will be attained as a function of I. The next comes the target tables T. The both prediction map as well as the target tables has a minimal value called an error value, which is called as the loss. So the last final part will have an input as a dot. So the input which is given is an image, and the output what we receive is a dot. So the dot shows the count of the cells which is present in the image. So this is the flow of dot, flow of cell counting, how we are going to do using our neural networks. First one is image input I. Next we are going to pad it. 0 padding is done. Next is our image input to our network. Next we are sending it to the convolutions where there are 32 convolutions, 2 of each sides, which predicts the map, which is our function f of I. And finally, if we find the target labels, and when the target tables T is found, we also found a certain loss limit E. E is equal to the difference between the target labels and the prediction maps T minus f of I. Finally, receiving that, we have got a dot input L, which is the counting of full cells. Cell counting images is a 3-planar image which can be predicted and identified through this particular. Next we have got the images, each and every side the image will be aligned together with the prediction map, target tables and dot input. The counting network increases from 2 to 16. So the predicted average count is 29.4. The cell and the FCR and count section is 28.9. So finally, with the error value is 8.8 plus or minus 2.3. So the optimized result has been obtained using regression target and the predicted counts. So the number of cells counted to be accurate. Next is the input image of a cell, tumor segmentation cell, which has a regression target and predicted counts. Next, we have got a Kaggle data set, which includes a C-line chain challenge, that is, on an image, how many number of adults, subadults, female, juvenile, and pub are there. So the predictions and the target has to be identified using our convolution network algorithms. So next, we are coming back to semi-supervised segmentations with GANs, generative networks. Next is image with segmentation labels and images without segmentation labels, generative adhesive network. Next is semi-supervised segmentation with GANs. Annotated image sample, we have got unannotated image sample, forward propagation, segmentation probability map, truth map, evolution, etc. So next, there is an image. Actually, that image can be shared and measured easily. Each and every input image has a grayscale. Next comes the ground truth. Next is our SN. Next is our SSAN. Next is ladder networks. The final one is DAN. So each and every image has a different set of actions and active points that has been represented using these models. The next, genomics. Next, we are going to see what are genomics. Important findings of human being, which is very important in our human creation. This is the total genomics, which is the translation, per exome, metabolism, amino acids and biosynthetics, RNA processing, chromatin transcription, cell wall, etc. So in machine learning and artificial intelligence, we have used in genomics to analyze vast amounts of genomic data, identify patterns, and make predictions. Ultimately, which helps in benefiting the research, healthcare, and disease understanding. So these ML algorithms can learn from data, identify connections, and offer insights that would be difficult to discern through traditional methods. So gene annotation, this includes gene annotation, functional analysis, disease risk prediction, target discovery and drug development, genomic prediction, cyclomagic analysis. So GenoML, the example of ML which is used is GenoML, which is developed by NIH to help researchers identify patterns in genomic data related to disease. Next is deep learning. So benefits of using ML in genomics is enhanced data analysis, which helps in handle complexity and volume of genomic data. And also it gives improved prediction accuracy, which is faster discovery, personalized medicine, and it will help us in dealing with computational methods easily. So there are factorized embeddings which has to be found out. Input, what is the input we are going to give as tissue index? This tissue index has been given to the neural network, which is concatenated, which is fully connected through hidden layers, and then we have a gene expression. So first tissue index is given, next gene index is given, genes has been embedding space. So combining this tissue embedding and genes embedding, we concatenate these two and we fully find a hidden layer. There may be more, we cannot predict the number of hidden layers which is present inside. So it may be more than 10, which is stan of H, and it is a gene expression. So the types which is used in genomics, what are the types we can input as a data set is artery, coronary, tibial, mammary tissue, atrial appendage, left ventricle. These are the parts where we can identify the genomic representation and we can take a data set for that. For example, the breast cancer, heart patients who have got heart attacks, who are suffering from strokes can also be found out. Next is breast, heart and uterus, mammary tissues, artery appendage and left ventricle. Here, these are the places where we can identify the genomic diseases which is present, and we can collect the data and we can have a data set, and we can use this deep learning concept to predict, analyze, classify and optimize the solution. Finally, we can visualize each and every expression level which has been present for every tissue embedding. What is this gene involved? There are genes. We know what is genes is. Without genes, each and every human being cannot exist. This has been carried over from descendants. We are carrying over from 2,000 years of experience. We have been carried out from more than 5,000. We cannot even predict. For example, we Tamilians are bound to more than 2,000 years of Tamil language. Likewise, this gene is it's a particular word with particular point which has been carried out long lasting. So this gene includes tissue, gland, bladder, blood vessels, breast, esophagus, heart, kidney, liver, glands, all types of glands, pituitary glands, pancreas, ovary, spleen, stomach. All these has been involved in this genomics. So MYH6 is an algorithm which is devised in help of a doctor to find out using this CNN for prediction of diseases in blood vessels, colon, esophagus, heart and muscle. Keratin. The next one is keratin. Keratin is the protein that protects epithelial cells from damage or stress. So whenever we have got stress, we used to talk that I'm full of stress. What am I supposed to do? This is because of the keratin. So this keratin will help us to relieve us from the stress. So this keratin is mainly present in colon, esophagus, lung, skin, and small intestine. The high concentration of stress only goes with skin, small intestine, lung, colon, and esophagus. This is all about the first part, what is survey of medical imaging. That is, medical images includes not only I have given a view only on 4 sort of things. It is, for example, a tumor. We have spoken only about tumor, x-rays. There are more than this. Each and every part of a human being can be analyzed, and the data set can be used to have a prediction of disease in humans. So this deep learning plays a vital role in prediction and analysis of diseases, because the day-to-day life has increased with the diseases. The technology also has increased. The disease also has been increased. So for the pathological report, all we need is a machine learning and deep learning process which has to be implemented successfully. Next, how is Python is used in medical imaging? So what are we doing? We are doing only practical and theoretical skills in medical image analysis. Hope so. It is imaging modalities, segmentation, registration, image understanding, visualization. So we are establishing so many methods and research to understand using the algorithms. So why is medical image analysis special? Because of the patient. So the computer vision is good at detecting irregulars. For example, when two members are walking on a factory floor, but no 2 patients are alike, everyone is irregular. So when we go to a hospital, each and every member suffers from different type of diseases, symptoms. It is not common. Whenever it is common, we go for a huge, for COVID, for example, COVID. It doesn't show the same symptoms for every people everywhere. It was different from place to place. So the computer vision is very good in detecting irregulars. Next, medicine is a war. So radiology is primarily a reconnaissance. Surgeons are the marines. life or death decisions made on sufficient information. So whenever the reports are given, doctors maximum makes reports on only by the machines given. The radiology reports given by the radiologist only makes the doctor to analyze. So machine plays a vital role in analyzing the pathological report for the doctor and for the welfare of the human being. So we are not in any theory land anymore. So next is, what do I mean by analysis? So it is different from image processing, which results in identification, measurement, or judgment, produces a number of numbers, words, and actions. So complete image understanding automated within a computer to perform diagnosis and control robotic intervention is called as an analysis. So the machine will be able to understand the image completely, even if it is a RGB image or a grayscale image, whatever the image what we present, it understands the image completely and automate within itself, which is the machine learning algorithm to analysis and a controlled robotic intervention to do a particular action. So we all know nowadays the surgeries are made by robots. The knee transplantation, heart transplantation, lung transplantation, kidney transplantation. For example, the heart, the open heart surgery was a huge task in, for example, in South India, we do have a open heart surgery which is done for literally for 12 hours, which executes some speeches of 14 to 15 speeches in the chest, and by taking a vein from a leg or a hand, it also includes the total number of speeches runs from 15 to 20. So these switches has been reduced by the intervention of robotics, where the machines do a 3 drilling hole in the heart, and from the far front, the topmost, it puts the vein which has been removed from the leg, and then it is inserted, and then another arm through the third part, the third hole receives the vein, and it makes the heart to pump correctly. So it was done by a machine. Only 3 holes has been used without making switches, but it is not about currently. It is not in to say it is only in Chennai. Currently, we are not using end south zones. So if we want to use this type of medical history, we are going to a proper hospital, proper higher end hospitals. So in cities like Bangalore, Mumbai, and Delhi AIIMS, it is very fast enough. They have started to use robotics in implementation for transplanting heart, lungs, everything, kidney, etc., etc. So this is the state of art, which results in segmentation and registration. So first part is segmentation. As we have already discussed in various previous records in the previous slides, the segmentation is labeling, which may be discrete or fuzzy. So discrete, we know it is a huge number of numbers, or some data which runs from 000 to something 0, any numbers. But fuzzy includes only it will be zeros or ones. How good are such labels? So we'll only check with gray matter versus white matters. So gray matter are called as circuits, and white matters are called as cables. So this is the tremendous oversimplification of the labels has been required to deliver a model. The second part is registration, image to image, same versus different imaging modality, same versus different patient, topological variation, image to model, which helps in deformable models. Next is model to model matching graphs. So we'll have graphs matching. The third one is visualization. So visualization means to picture in the mind. Retina is a 2D device which analyzes to visualize the surface. So a doctor always prefers a slice to rendering his visualization. So it requires a visual cortex. So computers have an advantage over humans in 3D. So we are watching only 2D images. Our eyes only shows 2D, which is X and Y. But machine is allowing us to see a third dimension of a human, which helps in retrieving so many data. So the model of a model radiologist is radiologist. We are speaking about the radiologists, the people who scan who's employed MRI scan, Doppler scan, whatever the scan, X-rays, whatever it is, whoever it is, they are called as radiologists. The radiologists have a flow graph of data acquisition and image construction, which has gone into a mission of semi-automated image analysis. On finding, also he also have a set of database which identifies, which is correlating with the database already he has, and then display the image and associated information. Then also he goes for the medical history of the patient so that he is able to correlate all the data which is available priorly in our data set. This is what the dictation and rounds through the procedures. So how are we going to do this? There are two ways. One is a shadow program. Next one is project oriented. The shadow program is observe and interact with the practicing radiologists and pathologists at any hospitals. That may be, you may be go in person or you may be visiting through an online session or whatever it is. It is called as a shadow program. So when we come to project oriented, we are going to get all the data sets and we are going to implement either in C++ or Python, whatever it is, any programming language we can go into it. Now we are going to see how Python works with these type of images. So before entering into the applications of Python in healthcare, I would like to give you an example of when we collect a collection of recipes. Okay, a box of tools which is not a program actually, which is where there are records present. It is a record. We can take the record, we can check it out, but we cannot make an analysis. But when we go for a software project or a program or a solution, we can have an analysis, we can have a prediction, and we can give a prediction so that it can be cured as fast as easier. So this computer programs that is fully and semi-automated programs is very application specific, and there is no general solution because under the supervision and apprenticeships of machines, it is completely 100% pure because machine is a slave. You know, whatever the data we feed them, it gives us a reliable output. So now we are going to see in 10 ways how Python is implemented in the healthcare field. We all know Python is an advanced, versatile programming language that develops algorithms to process and analyze images. So first one is detecting Parkinson's disease, the highly used where this Python has been implemented successfully or in detecting Parkinson's disease. So this machine learning algorithm using this MRI scan of patients has given out a very good result for this Parkinson's disease. Second, it is used to analyze data because usually we have got more number of data in healthcare. So each and every day we can have n number of patients for an hospital with n number of complaints. So the data has to be stored and analyzed by the hospital each and everywhere to have a better patient care and develop newer treatments. It is also used for building healthcare models used ML. It also uses an AI to inspect, break down the patient data that has been collected to forecast predictions. Moreover, using the Python libraries like SciPy, NumPy, Pandas, we can develop a huge machine learning models to analyze data. Next is used for making predictions, as we have discussed earlier in the tumor prediction, no tumor prediction, necrosis, chest, in all type of segmentation and all type of pathological analysis, we can use these predictions, which is very effective using this Python. So they can also have the probability of patient responding to a particular treatment and forecast hospital admissions. The fourth one is automated medical imaging in CT scans. See, the scans, what we use is, we have got different types of scans. So while using CT scans, this has been 2D slices of each and every patient brains. Most probably we'll have CT scan for our brain, abdomen or chest. Okay, so all the brain will be shown as a slices of each and every part of our brain will be shown as a slices. So this will help to analyze a 3D image series from a CT scan. So for example, I'm saying our brain can be scanned with 24 slices of scan results, 24 slices of brain. So when we support this, when we put on this data to a deep learning algorithm, this all 24 is combined together and to form a 3D image series so that it will reveal what this brain has been gone through, or whatever it has been, may be affected, may not be affected, whatever the solution is, whatever the prediction is, will be given. This is what it is done through algorithms to an integrated application that can analyze chest, spine, abdomen, head scans without depending on an application for image analysis. Next is boosting the speed of MRI. MRI is a very interactive scanning what we are using nowadays. It is a non-destructive way of examining the internal working of the body. So it will show the internal working of the body. It is comparatively less risky than a CT scan, but takes longer examination time. So, for example, performing a cardiac MRI may take more than an hour. With image-based machine learning, the time taken to conduct a cardiac MRI examination can be reduced. So, when our images using MRI scan is given through a machine learning, automatically it starts scanning, it starts giving predictions. Next is enhanced PET scan accuracy. PET scan is a drug tracer used to detect normal or abnormal metabolic activity in the human body. These scans are helpful in evaluating patient response to treatment, especially in cancer cases. So, additionally, we have got early detection and response play a major role when the patient undergoes chemotherapy or radiation therapy. So, in helping cancer patients, this machine learning and deep learning plays a vital role using Python. So, Python is very easy for us to use because of the available flavors and the platforms, and the Flask which is available is very comfortable in using. So, we go for enhanced PET scan accuracy using Python. Next is improved ultrasounding image. So this develops patient to self-scan, capture ultrasounds to aid them in treatment or conditioning. Next is automated X-rays. So now algorithms are powered by Python to detect symptoms of tuberculosis through X-rays. The Python program has been implemented to detect symptoms of tuberculosis through X-rays itself. X-rays is a picture which is a black and white picture which has been scanned and which is given in a sheet of paper. Now the X-rays is been automated using Python to detect tuberculosis. So it helps in identifying abnormalities accurately. So it is very helpful to radiologists. Because of this technology, we were able to help the patients in early stages and decrease the mortality rates. Improved image analysis software. Next is improved image analysis software. A software is written in Python and has been implemented in all scan centers. Apart from their MRI apps, this is a separate AI which has been developed and which has been implemented in certain American and United Kingdom hospitals to find for the helpful payment of radiologists and clinicians. Also, now radiologists will spend less time screening images, which in turn will allow them to focus on patient diagnosis and decision making. So it is very helpful in decision making. The intelligence provided by this AI-powered image analysis will help paramedics and doctors to interpret images from the ultrasound scanners. Finally, timely and accurate diagnosis. So it is very helpful. This particular algorithms which has been developed using Python so shows the advanced image analysis techniques, which is very helpful for the patients and to avoid the time and accurate death diagnosis. This was highly effective. So this is how the function of the usage of Python in 10 areas. So that these 10 areas also focuses on these three individual analysis part, which is segmentation, registration, and visualization. Already we know all the algorithms which is available in Python will help us to classify. First it will clean, first it will pre-process, next it will classify, next it will predict, and it will give us a result. So this mostly we all use prediction algorithms in this medical imaging sector using these three important functions. First one is segmentation, registration, and visualization. So with this, I wish to conclude my session of a survey on a survey of deep learning approaches to medical applications and Python in medical imaging. Thank you. Thank you.
Thank you, ma'am. Any queries from faculties?
See, I have thrown only what are the areas in which we have worked. There are still more areas and still more programs. Since my screen is not visible, I'm not able to show you the Python program which has been executed for this cancer patients. I'm extremely sorry for the inconvenience that has been come.
Okay, ma'am. Next session we'll allocate another one session, ma'am.
Please send the presentation, ma'am.
Sure, sure. I'll send you the presentation in the.
We cannot be able to ask any queries.
Yeah, they can ask any queries. No issues. I'll send you the presentation.
Okay,
Thank
sure.
Thank you for having me. Thank you.
Thank you, ma'am. Thank you for sharing your valuable insights, ma'am. Thank you, participants.
Thank you.
Ma'am, kindly send the PDF today itself, ma'am. Hello.
Yes, ma'am. I'll send it. Ma'am. Shall I send it in WhatsApp, ma'am?
Sure, send me in WhatsApp.
Okay, fine. Thank you.
Okay. Yesterday class also we can get PDF now.
That has to be asked from the organizer, ma'am. This is me, the presenter. I'll share you the PDF.
Okay, sure. Thank you.
Thank you. Thank you so much, ma'am.